Okay, so determine whether each of the following series converges or diverges. We only have 3 tests to use so far: geometric series, the test for divergence, and the integral test. Okay, so the sum from n equals 1 to infinity of 2n over 3n plus 1. It's almost always advisable to start writing out some terms. So it's a good first step almost no matter what you're given for a sum. So if I plug in n equals 1, I get 2 over 4. Plug in n equals 2, 4 over 7, 6 over 10. And then I notice that these don't seem to be going to 0 very quickly. So I'm going to go back and think about, what do these approach as n goes to infinity? This is a rational function. The degree of the numerator and denominator is the same, which means eventually these terms are going to approach 2/3, the ratio of the leading coefficients. So eventually I'm just adding basically 2/3 over and over and over again, which means that this sum is going to grow without bound. I am just going to be adding more and more and more, and it's getting bigger and bigger and bigger, growing without bound. So to formally write this out, I would say the limit as n goes to infinity of the terms 2n over 3n plus 1 is 2/3, which is not 0. Thus, my conclusion is that the sum, my original sum, diverges by the test for divergence. Okay, for B, again, start by writing out some terms. So 50 times negative 0.4 to the first. 50 times negative 0.4 is negative 20. And then I'm going to do 50 times negative 0.4. I should put parentheses around that. Squared. And I get 8. And then I'm going to cube it. And I get negative 3.2. So negative 20, 8, negative 3.2. We'll do one more. I'm going to plug in the 4th power. And I get 1.28. Okay, so the terms are going to 0, so that's good. They're bouncing between positives and negatives, but they're getting smaller and smaller and smaller. So I cannot rule out convergence. So what I might notice, though, is that you're multiplying by negative 0.4 over and over. So times negative 0.4, and then you're multiplying times negative 0.4 again, and then times negative 0.4 again. So this is a geometric series, and my constant multiplier of negative 0.4 is between negative 1 and 1. So this converges. So my conclusion is that this sum from n equals 1 to infinity of 50 times negative 0.4 to the n converges by the geometric series test. Okay, the sum from n equals 1 to infinity of ne to the negative n squared. If I write out a few terms here, if I put in n equals 1, I get 1 over e to the negative 1, which is 1 over e, right? And then if I put in a 2 for n, I get 2 over e to the 4th. 2 squared is 4, move it to the denominator, yep. Then I'm going to put in a 3 for n, and I get 3 over e to the, so that would be negative 9 e to the 9th plus dot, dot, dot. All right, so those do look like they're going to 0, so I can't rule out convergence. But it is not geometric. I don't have a constant multiplier. And the only test I have left to me right now is the integral test. So I need to compare to what the integral does. I want to say, what does the integral from 1 to infinity of x e to the negative x squared dx do? Okay, because the function f of x equals x e to the negative x squared is always positive and decreasing, the sum from n equals 1 to infinity of n e to the negative n squared will have the same behavior as the integral. So next step is I need to figure out what does n e to the negative n squared, I'm sorry, what does the integral of x e to the negative x squared dx do from 1 to infinity? So I'm going to get a new slide to work on this. So the integral of x e to the negative x squared dx, I didn't put any bounds on here. I'm just going to work on finding an antiderivative first, and then I'll evaluate with the bounds. So I'm going to let u be negative x squared. I'm using u substitution because I've recognized that x squared is the inside of a composition, and its derivative also appears in the integrand. So u substitution is a good bet here. So if u is negative x squared, then du dx is negative 2x, which means dx is du over negative 2x. So this is the integral of x e to the u, and then instead of dx, I have du over negative 2x. The x's cancel, and this becomes negative 1/2 times the integral of e to the u du. Take the antiderivative of e to the u, and I get negative 1/2 e to the u plus c, and then plug in the original u. So this is negative 1/2 e to the negative x squared plus c. There's my antiderivative. Now I can put on some bounds. So I want the integral from 1 to infinity of x e to the negative x squared dx. Now I know the antiderivative of x e to the negative x squared is negative 1/2 e to the negative x squared, and I'm going to evaluate that from 1 to infinity. The way you evaluate this is instead of going from 1 to infinity, you go from 1 to b and take the limit as b goes to infinity. So I'm going to take the limit as b goes to infinity of negative 1/2 e to the negative x squared evaluated from 1 to b. So this is the limit as b goes to infinity. First, I'm going to plug b into my antiderivative. So I get negative 1/2 e to the negative b squared. And then I'm going to plug a 1 into my antiderivative for x. So I have negative 1/2 e to the negative 1. And when I let b go to infinity, this first term goes to 0. And I'm left with, so 0 minus a negative, so plus 1 over 2e. So 1 over 2e is the value of the integral, which means the integral converges. So the integral from 1 to infinity of x e to the negative x squared dx converges. I happen to know what it converges to, but that doesn't help me very much with the sum because the sum doesn't converge to the same number. We just know that it also converges. The integral converges, so must the sum, because we satisfied these other properties where the function is always positive and decreasing. Okay, so that means that my original series, the sum from n equals 1 to infinity of n e to the negative n squared, also converges because its associated integral converged, so by the integral test. Okay, earlier in the term, we saw the following result when we were studying improper integrals. If you integrate from 1 to infinity, 1 over x to the p dx, it converges when p is bigger than 1 and diverges for p is less than or equal to 1. So we get the following analogous results for series. If you add up the 1 over n to the p, infinite sum 1 over n to the p, it also converges when p is bigger than 1 and diverges when p is less than 1. So it's really important. We use it a lot, and we call it a p-series. So I will let you read these samples on your own, and we are going to jump down to these p-series test problems. And then we want to determine whether these converge or diverge. So first, I'm going to note that the -4 makes no difference. I can pull it right out of the sum. So this is 1 over. Now, the fifth root, you put that in the denominator of the exponent. So this is r to the 3/5. And I would say that we know that this is -4 times a p-series with p equal to 3/5. Since p is less than 1, my sum diverges. Okay, again, the 17 does not really matter. Pull it out of the sum if you want. Okay, this is a p-series. It is 17 times a p-series with p equal to 8. Since p is bigger than 1, my sum converges. Okay, last one. Pull the 3.2 out. 3.2 times the sum. The starting point doesn't matter at all because if it's convergent or divergent starting at 1, you can subtract 72 terms and it will still be convergent or divergent. If it was finite to begin with, subtracting some finite number of terms will let it continue to be convergent. If it was infinite to begin with, subtracting a finite number of terms, you still have infinity. So you can, the counter where you start at the index, it doesn't matter. So this is 3.2 times a p-series with p equal to 0.99. Since p is less than 1, the sum diverges. Okay, so we've got 3 more here. We want to determine whether they converge or diverge. And again, we only have 3 tests to use: geometric series, nth term for divergence, and the integral test. So 1 over 1 plus n squared. It looks so much like a p-series, but it's not a p-series. If it was just 1 over n squared, I could use the p-series test and be done, but it's a little bit different. So instead, I'm going to use the integral test, and I'm going to note that 1 over 1 plus x squared is always positive and decreasing. So I can use the integral test. Okay, so whatever the integral does, the sum will also do. So I'm going to evaluate the integral from 1 to infinity of 1 over 1 plus x squared dx. I could do this directly like I did in the earlier example, get an antiderivative, evaluate from 1 to infinity. The antiderivative is arctan, so it's not too difficult. Or I can compare to 1 over x squared. I'm going to compare to the integral from 1 to infinity of 1 over x squared dx, okay, which I know converges. Okay, so 1 over 1 plus x squared compared to 1 over x squared. Larger denominator makes for a smaller fraction. So that means that all of the y values for 1 over 1 plus x squared are smaller than those for 1 over x squared, which means that the integral from 1 to infinity of 1 over 1 plus x squared dx is smaller than the integral from 1 to infinity of 1 over x squared dx. So the integral from 1 to infinity of 1 over 1 plus x squared dx converges because it's smaller than a convergent integral. So if my integral from 1 to infinity of 1 over 1 plus x squared dx converges, then my sum converges. The sum from n equals 1 to infinity of 1 over 1 plus n squared converges by the integral test. Okay, 2 times 7/6 to the n minus 1. This is geometric. We're multiplying by 7 over 6 over and over and over, with x equal to 7 over 6, which is bigger than 1. Therefore, my series diverges by the geometric series test. All right, last one. I'm going to start writing out some terms here. If I plug in a 1, I get the sine of 1 plus the sine of 2 plus the sine of 3. I don't think that these are going to go to 0. Let's see. If I take the limit as n goes to infinity of the sine of n, the sine function looks like this, right? It never settles down to a single limit. It kind of bounces between -1 and 1. So it doesn't have a limit. The limit is definitely not 0, which means the integral diverges. I'm sorry, the sum diverges. So my conclusion is that my original sum, n equals 1 to infinity of sine n, diverges by the test for divergence.